This screencast is looking at Worksheet 8F, Problems 3 and 4. So in this worksheet, we're starting to look at quantified work and power. In other words, work in the amount that we can calculate. So let's look at example 3 first. We've got a cat who pushes one of those small little cat toys, a 25-gram ball, and makes it was originally at rest, and the cat, when it pushes it, gives it a speed of 4 meters per second. And we want to know how much work did the cat do on the ball. So if I'm looking at a system, which is the ball and the earth, originally the ball is at rest, and it's on the ground, and at the end the ball is moving at 4 meters per second. So if I think about what kind of energy did this system have in the beginning, well, I think that it really didn't have any mechanical energy, right? The ball is at rest, so there's no kinetic energy. The ball is on the ground, so it has no height. There's no gravitational potential energy. And so basically there's no energy to begin with at position A. But at position B, it's moving. It's still on the ground, so there's no gravitational energy, but there is kinetic energy because now the ball is in motion. That energy had to come from somewhere, and energy was added to the ball's system by the cat. The cat did work when the cat pushed the ball and made it move. So there was work that transferred energy into the system. I need to show that as an arrow pointing into the circle with the letter W next to it to say that the way the energy was transferred into the system was by the process of working. In other words, someone from an external system applied a force that caused something in the system we're looking at to move. So the conservation equation here would be that the work that the cat did equals the change in the kinetic energy of the ball. Okay, and they're asking us to calculate how much work the cat did. So how much work did the cat do? So I'm going to go over here to the right, and I'm going to rewrite the kinetic energy, or I'm sorry, the conservation equation. So if I could calculate the change in the kinetic energy of the ball, I would know the work, right? And I have a formula for that. It's half of the mass times the velocity squared. And so let me just plug in here. Now I want to be careful to make sure everything is in standard units before I plug in. And the mass is very small. It's in grams. I need to convert that to kilograms. So 25 grams, and there are 1,000 grams in every kilogram. And so that would be 0.025 kilograms. Very, very small. So 0.025 kilograms, and then times the 4 meters per second squared. That's going to be the amount of work that the cat did. And it's only 0.2 joules. Because it's a very, very little ball. Okay. So in this example, in order to calculate work, we didn't use a formula for work itself. We were able to infer how much work was done by looking at how the energy of the system changed. And let me just say that again. Here, we inferred how much work was done by looking at how the system's energy changed. Okay, let's look at the next problem, number 4. It also involves a ball, and here the ball is a soccer ball that has a mass of 0.3 kilograms, and a soccer player pushes it with their foot, and they impart a force of 250 newtons and move the ball 0.25 meters. So look at this. They're imparting a force and moving the ball. So they're telling us both a force and a displacement. And here we might be able to use our formula, which says that work equals the force times the displacement. But let's keep going. And here we want to find the soccer ball's speed immediately after it's kicked. And so we're going to take the system to be the ball and the earth, which is very similar to the system that we had in number 3. At the beginning, the ball is at rest on the ground. And at position B, we're going to say the ball is moving. We don't know how fast yet. And it's still on the ground. So at the beginning, that soccer ball really didn't have any kinetic energy. There's no gravitational energy because it's on the ground. There's no kinetic energy because it's not moving. And at the end, it has kinetic energy because it's moving. That energy came from the work that the soccer player did on the ball. The player is in a different system, an external system. They applied a force to the ball and caused it to move. By doing that, applying a force and causing it to move, they transferred energy into the system that has the ball. And so we end up with exactly the same energy conservation equation that we had in problem 3. The work that the player did on the ball equals the change in the ball's kinetic energy. And I'm trying to calculate the speed immediately after it was kicked. So I'm going to write my conservation equation. And I'm going to plug in or substitute in the method, the formula that we could use to calculate each side of this equation. I can find work by multiplying the force times the displacement if I'm given those things, and I was given those things here. And I can calculate the kinetic energy at position B by taking half of the mass of the ball times its velocity squared. They're asking me to find the speed. So I'm going to solve for the V at position B. Okay. So let's see if I have everything else in this equation. The force was 250 newtons, and that force was applied while the ball moved 0.25 meters. The ball's mass is 0.3 kilograms, and then of course I'm going to solve for V. Okay, so V is going to be the 250 times 0.25 divided by 1/2 and divided by 0.3. And then I really want to find the V, not V squared. And so I'm going to have to take the square root of this. Okay, and let's see what we've got here. And we get 20.412 meters per second. So in this situation, we had information about the force and the displacement, and so we could use this formula here to calculate the work.